very clearly spelled out calculation where you can really follow all the details if you just sit down and do it on a piece of paper. And this was actually, I mean, that part of the paper was actually explicitly done by Tommaso.
So there might be typos. So.
Okay, so
okay, thank you very much, Stefan, for this very nice introduction. So, okay, hi everyone. So first questions, how many of you are kind of familiar with coding in Python? Okay, good, most of you. So the idea of these tutorials is the following. Basically, we will we have some collab notebooks. So in order to access them, I'll put now in the Zoom chat. Actually, maybe I've done it already. A link, and following this link, you should be able to open the notebook you see now on the projector. So actually, are you connected to Zoom? Okay, so can you connect to Zoom? So I'm also not. So should I send you the link? Okay. Okay. Meantime, you can see all my emails. So, okay, while we set this up, let me introduce a little bit what we are gonna do. So basically, we are gonna start from where Stefano left. And the idea is to basically look at this little code that we have in this notebook and try to understand which are the main ingredients and how to use them when we perform a fit of Parton distribution functions. So while Alessandro shares the link, so let's set up the stage. So you have seen in the lectures that we can write down the structure functions in the IS as the convolution between some Wilson coefficient, which will be function of the hard scale, well, of the ratio between a hard scale and the renormalization scale, the coupling, and a set of Parton distribution function. So first question, looking at the right-hand side of this equation, what can you compute by hand? Question. Okay, good. So the coefficient function and and something else, which is, so if you look at this object, it is a function of the factorization scale, right? And actually you can compute the dependence of the PDF on the factorization scale. So in particular, you can choose a reference scale, mu0, and you can write this object as the convolution between a certain kernel, ij, which brings you from an initial scale mu0 up to scale mu, convoluted with your PDF at the initial scale mu0. Okay, so actually in this equation here, you can compute the Wilson coefficient and the dependence on the scale of the PDF by solving the RG equations you've seen this morning. It's still there. Okay. So this in Milan, here is Milli space. Then if you go back in X space, you get this. Okay, fine. So this you compute, what about this? So what about the boundary condition of your RG equations, basically? So what about the X dependence of the PDF? So this cannot be computed from first principle, at least within the framework of perturbation theory. And so what you do is that you extract them from experimental data. So the idea is the following. So you have data for this object, right? You have experimental measurement giving you central values and uncertainties for example, structure function in the IS. So the idea is that you parameterize this object in terms of a certain number of free parameters, you compute the theory prediction as a function of these free parameters, and then you fit these free parameters to the data, okay? So you start from parameterizing the X depends of the PDF in terms of a number of free parameters theta. You use this formula here to compute theory prediction for this guy, again as a function of theta. From this you compute some loss function, and then you minimize to this loss function, finding the values of theta which best fit the data. Okay, so in the notebook we are going to do this, and in doing this we will see how we parameterize the PDF. Then how do we actually compute this convolution during the fit, how we define the loss, how we minimize it, and then also how we propagate the error in all of this. Okay, we are trying to determine a continuous function, but we don't want only a central value. We also want to provide some uncertainty to our result. So the idea is that in this simple notebook we will cover all of these aspects. And the idea is that so first we will introduce together the main players in this exercise. We'll comment on most of them, and then there are some exercises you will have some time to try to do them. I mean, you can do them together, I mean, whatever, some finite amount of time to do the exercise, and then we will discuss the solution together. So it's not really, I don't want you to learn how to code. I mean, either you know already how to code, or it's not me who are gonna teach you in an hour how to code. It's more that I want you to understand the concept and maybe to be able to play around with this code a little bit by yourself. Cool? Questions? So on your laptop, do you see this notebook? Very good. So, okay, so let's start going through it together. So what do we need in order to, first of all, so we are gonna consider a very simple case. So if you look at this equation, you see we have a sum over I, where I is the flavor index of the PDFs. I don't know how much you know. I mean, for each quark, each intrinsic component of the, well, also not intrinsic, for each component of the proton, we have a PDF. So in this case, in a realistic PDF fit, we will have, let's say 8 flavors, sometimes 7, sometimes 9. In our case, we will have just one, because we will consider a very specific data set that we're going to discuss in a moment. And this is just for a matter of simplicity, okay? Just to have something which we can do here. And actually, this is a simple yet not yet quite realistic case. In fact, we will basically try to reproduce the results of this paper, which was written back in the days by Stefano and some collaborators, and I think it was basically one of the first NMPDF papers. So it's where this methodology was first developed. So let's start looking at the first ingredient. The first ingredient are actually the experimental data that we're going to consider. So if you execute this first cell, yeah. So basically, you're gonna, yeah, this is gonna clone this repository that you can actually find on my GitHub. Yep. So how many of you can see this notebook? Okay, good. At least one. Giusto, giusto. Mo può scrollare giù.
Dovevo andare giù.
E se clicca qua, avviso, sì, non è Google, ma sono io, quindi è sicuro.
Scusa, invece ero rimasta sopra.
All good. Okay, so with this first cell, you clone a bunch of stuff, which is saved on GitHub. If you have GitHub, you know what's GitHub. You can visit my profile. You will not find anything interesting, but you will find this repo where you can find this material. And in this cell, we start loading the experimental information. So we load the experimental information as NumPy objects. So what do we load? When I say experimental information, what do I mean? I mean a set of central values and then the uncertainties. And the uncertainties for the data that we consider in a PDF fit usually are given like covariance matrices. Okay, so Gaussian uncertainties basically. And here you're also loading the kinematic. So the kinematic variable for the IS are x and q squared in this case. And in this cell here, we are plotting basically the kinematic coverage of this data. So this is the kinematic coverage of the data which we'll consider in the fit. So in this plane, you have x and q squared. So what does this mean? So if you click here, you're redirected to a paper where a real fit of PDF is done. And if you go to page maybe 10, yeah, 10, here you see a realistic kinematic coverage for a real fit, a real global fit. So here again, you have x and q squared. And basically, you can see that in real life, we go down until almost 10 to the minus 5, very high energies, especially with jets and stuff. And so basically, with this exercise, we are considering just a very small subset of data here. So of course, we will have a much more limited constraining power because we have just a small amount of data. We're considering around 200 data points. These are more than 4,000, I think. So this is just to put things in perspective. This is what happens in real life. And if you go back to our little notebook here, this is what we are going to consider here. Okay. Now, what kind?
This is what happened in real life, like 25
Yeah, of course. So this paper is from 2007 to 2007. Yeah.
but BCDMS, I don't know, you also use NMC data?
No, just BCDMS.
So this is even 30 years ago. BCDMS is 1990.
Yeah. So I was not born when this, and neither were you. So.
BCDMS is an acronym of it's Bologna, Colombia, and I forgot the rest. It was a CERN experiment with muons, a muon beam, which was produced by hitting protons, producing protons,
Yeah.
SPS protons on a fixed target that produced ions, and then decayed and produced a muon beam, and the muon beam was used to do inelastic scattering on a fixed target. The target was either a proton target or a deuterium target.
Or deuterium, actually.
This is the difference between proton and deuterium, because then this is something I did not have time to discuss this morning. But anyway, if you take this difference, everything else goes away, and only one part of distribution is left.
Yeah, exactly.
No, it's the contrary. NMC was called the new muon collaboration because it was new in comparison to BCDMS. BCDMS ended in 1991, I think, and then the NMC collaboration was born, which was the continuation, and it was new because it was new after BCDMS. And by the way, I mean, just for historic interest, BCDMS was the first ever at the time precision measurement of the strong coupling constant, which was done by two French people, Berchot and Milstein, who were members of BCDMS, and for the first time, using the scale dependence of this data, they extracted the value of the strong coupling constant to an accuracy of about 10%, which at the time was very, very high.
Okay, so So indeed, as Stefano was saying, the main outcome of this experiment in terms of data are structure function on a proton and a deuterium target. It turns out that if you take the difference of this thing, you find out that this difference can be expressed as a convolution, like the one which is written there at the blackboard, between a single coefficient function and a single PDF that we will be calling T3, and that basically is U plus minus D plus, where Q plus means Q plus Q bar. Okay, so this is a very specific combination that we will be considering in this tutorial. It's the only one that we will be able to extract from this data. And what makes this really a kind of ideal toy scenario is that this T3 is a pure non-singlet distribution. So you've seen that the glab tells you how PDFs evolve with the scale. The point is that this evolution usually mixes different flavors among them. Non-singlet distributions are like independent, fully independent distributions, meaning that they evolve diagonally. They don't mix with the gluon or with other stuff. Okay? So this means...
Just a small comment, just to make context. In all the equations I had, I always had F2 divided by X. In Tommaso's notation, this extra factor of X is actually included in the coefficient factor. So if you wish, the coefficient factor is not a delta, but it's X times delta. Of course, because delta is delta of X equals 1, X times delta is basically the same as delta, but then the next leading order piece has an extra factor.
Sorry, there is no effect on the charges. It's really just one, or there is some...
If there is already hidden in C.
The factor is 4 9 minus 1 9. So it's 3 9, which is 1.
Yeah.
So it's not normalized to 1, but there is some normalization.
Okay. Up to this point, all good? Good. So now, before moving on, how do we actually compute this convolution? So when you do a fit, when you build the loss function, you take the data, you take theory predictions for your observable, and you build the chi-square, the loss function. Okay. This means that when you go through the minimization procedure, you have to compute the chi-square thousands of times. So if each time you do an expensive computation, you will never have a result from your fit. So in order to compute this convolution in a fast way, we will be used these FK tables. FK stands for fast kernel. So basically the idea is that you can expand the PDF, so T3, in that way, on an interpolation basis. So T3 is a function defined between 0 and 1, like all the PDFs. The idea is that you introduce an interpolation grid. At each point on this interpolation grid, you consider the value of the PDF, basically, and this is going to be these are going to be the values of the coefficients multiplying a certain interpolation basis. Okay, so this means that your PDF, up to some negligible interpolation error, can be written as a sum over alpha, where alpha is labeling these interpolation points. And then you have the values of the PDF on these points times these bases. So these are a set of functions, of continuous functions, which form a basis in the interval 0 and 1. Now, if you do this, and you substitute this expression 43 in your initial factorization formula, you see that basically you can take out from the integral T3 and the sum, and so you are left with this expression. So you have the sum over alpha of this guy containing the convolution times the value of the PDF on a specific point. And so basically you can compute this object once for all, you save it somewhere, and so basically you see you have, so at the end of the day, this guy here is a matrix. So you store all of these, and all your physics, if you want, is contained here. So if someone computes DIS at the next perturbative order, you have just to run everything in order to compute this once for all, and then you save it there. And so at the end of the day, this convolution here can be written as this fast kernel tensor. So this is a matrix in our case because we have just one flavor, applied to a vector, and the entries of this vector are the values of the PDF on the points of your interpolation grid. Okay? Yeah. So so yeah, I mean, yes. So let's say that there is a whole framework developed to do this. So in the first paper we were mentioning before, they took a basis which was basically a kind of triangle picked on each of these points. These are very crude, yeah, but it worked. So if it's really something that you can do in like 5 minutes in your little code, and it kind of works nicely, then you can, I mean, you look a little bit in the literature, and you find libraries which does interpolation for you in a very fancy way. I personally don't even know the details exactly. It's a, let's say it's a completely solved problem, and you can use external software. Yeah. But you don't have to.
Exactly. You know, it's a smooth function between 0 and 1, and interpolating a smooth function between 0 and 1 is a solved problem for which you can find.
X equal 1, you force it to be 0.
Yes.
So the basis contains the information that X equal
No. This happens at the level of the fit. So at this moment, up to this moment, you're completely agnostic about the PDF. So this is just a way to express the DIS convolution as a linear application applied to a vector. And the vector are the values of, well, of course, of the PDF, but at this level, the PDF is still a fully unconstrained function. So it depends on the data set. Right now, they are equal or lower than 50. But this is something that has changed. So this has been like this for the last couple of years. So up to 50, but then the idea is that you try, you see if you get something sensible, if you get crap, you reiterate. And the status right now is that we have 50 points, and a subset of these 50 points are used in all the data sets. Mm-hmm. So they're spaced logarithmically between 0 and 10 to the minus 1, and then linearly between 10 to the minus 1 and 0, I think. But they have to check.
0 means 10 to the minus.
Yeah, and 6, yeah. So basically, yes, exactly. So you have, basically you have to look at the kinematic coverage of the data, and you go down up to where you have points. Okay? Good. And so in real life, this FK is a tensor of rank 3. So data points, interpolation point, and flavor. In our example, it will be just a matrix because we have data points and interpolation indices. Okay, good. So first exercise that I hope it will take between 10 and 15 seconds, but I mean, no pressure. Is so you load the FK table, you load okay, this doesn't work because I've not run the previous cell. If it will work for you. So you load the FK table, you load the X grid of the FK table, which is this interpolation grid. And then you will also load this object F is just a reference a PDF taken from the literature, just to, because as we do the exercise, we will have at least something to look at, to check that our code is not producing random numbers, basically. So here you load the FK table, and then I thought somewhere here there was a first exercise. No. No, exercise 1, yeah. So the first exercise that you're gonna do later is just compute the theory predictions given this input PDF and the FK table. Okay, so what do? You have the FK table, you have the vector of values, you multiply the FK table times the vector, and then you produce then you have the data, and you produce a plot where you compare the data with the theory prediction. And you want to see that the theory prediction are within the uncertainty of the data. Okay? So it should be relatively straightforward. Now, so far we have seen how to compute this, right? Now let's say a few words about this part. So how do we parameterize is it everything clear so far? Like should be crystal clear. Okay, okay. Okay, but conceptually it's clear. Now let's move to how do we parameterize the PDF. So what we are actually doing is that we are trying to determine a set of continuous functions from a discrete amount of data. So we are trying to determine something which lives in infinite dimensional space from 200 points. So this is ill-defined, there's no solution. So we have to regularize the problem in order to make it solvable. How do we do this? One way is to introduce a parameterization. So we write down the x dependence in terms of a free set of parameters, and then we will feed these parameters to the data. So in order to do this, we will use a neural network. What is a feed-forward neural network? Maybe you know already what it is. I don't know. In simple terms, it's just, well, in simple terms, it is just basically a way to build a non-linear parameterization of your free parameters. So we wanna model a function, the PDF, which goes from R to R, right? A real function. So let's say that you take x, a real value. Then the idea of a neural network is that first you apply a linear transformation to this guy. So wx plus b, okay? And this guy is actually now in Rn, where n is some chosen value. Then you combine this linear transformation with a non-linear function acting on each of the n components of this vector. And then you reiterate. So then you will have again a linear transformation going this time from Rn to Rm. So let's call this guy here y. Okay, so you will have, and this is W1, B1, and then you will have W2 applied to y plus B2, and again you apply this nonlinear function. So you're stacking up linear transformation with nonlinear functions. This nonlinear function is called the activation function, and is what introduces the nonlinearity in your parameterization. Because of course, if you stack just linear transformation, you're just doing a linear transformation, all right? Okay, and then at the end, so this is in Rm or something, at the end, the final layer should send us back in R, right? Because we want to parameterize a linear function, and at the end we will have what we call, so we will have some function of x, which will be a nonlinear function of all these wi, bi. And if you Google neural network now and you look at the images, I mean, you always find this image like this, where you have all this layer. I mean, yeah, it's just a linear transformation. I mean, all these nodes represent the dimensionality of the space where you're going to. Okay, so this is everything we need to know. This is so it's a linear transformation. A linear transformation can go from R to Rn. It means that these are n parameters. So okay, this is okay. So R, if you want to go to Rn, it means that this W is actually a vector of n values. This is a vector of n values, right? Okay, and then when you go from n to m, then you have a matrix n times m. All right, and this is m, a vector of dimension m, and so on and so forth. It's just linear algebra, like, you know, when. Okay. So in literature, they're called weights and bias, and it's what I've been calling theta there. Yeah, I'm using different notations randomly without defining them. So fair question. Or threat, yeah. Okay. So so it depends on the problem. In real fit, we have in this moment, I don't remember, the first layer is about, we have 3 layers, I think, with 30, 20. So I think in total is 700.
Yeah, 700, almost 800.
Yeah.
But then 800 to parameterize.
Yeah, yeah, yeah. 9 PDFs, yeah. Funnily enough, you will see that I use incredibly high, very broad architecture. You could try to play with it and you will find out it's actually quite tricky also in this simple case to get a good result with a low. Well, there's a difference here and between here and real case. Here will be using just a neural network. Like in real life, we use also preprocessing polynomial term, which does give some structure to, so you have like x, so the real thing is like x to the alpha 1 minus x to the beta times the neural net. Here we only have the neural net. And if you, now we will look at the code now, and you will see that I use some insanely high number of nodes, like 64, 64, 32. So if you count them, I'm using quite a lot of parameters. But then you can try, but then you can try to play around. And actually, you will see that it's quite tricky to get the correct like a configuration of hyperparameters, so of all these things that actually produce nice looking plots to show in a tutorial. So, so you can try to play around, but this is also interesting because it shows you how you need an algorithmic way to make these choices for you, which is again what happens in real life, and maybe we will mention later. But okay, so up to this point, is it everything clear? Okay. So now in this cell here, you can see how you can actually implement this this kind of architecture. So we'll be using Keras. So actually for any, well, of course, for any question you can ask me now, but in general you will find a better answer if you look at documentation of Keras and examples and so on and so forth. But so the idea is that first here in this class you implement a linear layer. So, and this means, well, okay, to implement a linear layer, in a general layer in Keras, you have to define a build and a call function. In the build method, basically you implement the weights and the biases and you choose how to initialize them. So when you create your network, you have to initialize these 3 parameters to some value and you can choose different options for this. And then in the call method, the call method takes as input the inputs, which are basically real values in this case. And here you can see what it does. So it's a linear transformation of this input. Okay. So this is a kind of linear layer. And here in this class, which is called the PDF neural network, there's the actual implementation of the parameterization for the PDFs. So you see that we have 4 layers. Again, an insanely complex architecture. Probably if you do things properly, you could use, 4 parameters in total, but you can try, play with it. And then here in the call method, we combine them with the activation function. So you have the inputs. First, the inputs goes through the linear layer. Then we use the activation function, which is a ReLU function here. The ReLU function is a function which is a linear function for positive argument and 0 for negative arguments. You can play with these as well, and you will see that this has actually an effect on, again, on your training. So also here, this is another thing that one should choose when defining the methodology. And again, and then we apply the nonlinear transformation, then again, linear layer, nonlinear transformation, and so forth. And so on until we go back here. Okay. So at this point, you have a real function, real input. You go through the neural network, and you have your parameterization for the PDF. Now, in order to get the observable, what do you have to do? Exactly, FK table. And you can actually do this still. So the way in which is done this, in which it is done here, is by defining another layer where this happens. So you can add a layer on the top of your architecture that knows in its belly the FK table. You just put it there. And what this convolution layer does is to do this linear multiplication for you. This is a linear transformation for you when the real input has gone through the network. Okay? And so this is done in this layer, which is called compute convolution. And finally, in this class, observable, everything is put together. Okay, so again, you can look a little bit at the code, but you see that here in this class, I'm defining a PDF, parameterized in terms of neural network. Then we have a convolution layer which knows about the FK table, and what this object does is combine the two things. Okay, so at the end of the day, if you create an object like this, the output will be a convolution between your neural net parameterized PDF and the FK table that you've read in the previous exercise as a function of the free parameters of your network. Okay. Good. So once you have, so actually you can try to, if you run this cell here, you can run this. Well, you can do this when you do the exercise. So second exercise that you can do, and then maybe we stop a second, you try to do this two exercise, and then we go back to this, is to build the loss function. So far we have discussed how to produce theory prediction, how to parameterize the PDF. Last thing we need before running the fit is to compute is to build the loss function. So the loss function, we just build a standard chi-square. Okay, so I guess you all know what a chi-square is. So it means that, and so you can combine all the ingredients that we introduced so far in order to build this function. So you have data, you have theory prediction as a function of the free parameters. You combine the two in order to compute the chi-square as a function of the free parameters. And yeah, once you have done that, we go on. Okay. So I would say that now we stop for 10 minutes. I mean, stop meaning that I stop speaking, you start coding. And we see where you get in 10 minutes. Then I just give you the solution. And then we go on. And I mean, don't worry if in 10 minutes you cannot do, I mean, you cannot write the full function. I just want you to see all the concept today, and then maybe in your spare time or whenever. So, okay, exercise 1. So, compute zero prediction using, okay, other notation I've not introduced. So the reference value we have loaded here is from an PDF 4.0. So the first exercise was to produce theory predictions using the FK table I've given you and this reference PDF from the literature and compare it with the data. So in the first line, YTH means Y are the central value of the theory prediction is equal to, you have the FK table, which is a matrix, and you can just apply it to this vector of values of the PDF. Okay? So this should, let me run this. blah, 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 blah. So I load the stuff here. Now, if I do f shape, so f is a vector with 50 entries, okay? What are these 50 entries? Are the values of the PDF on the interpolation grid, okay? So it's, well, whatever, okay? Then, let's see FK shape, 2048 times 50. So what's 2048? I've not told you, but you can guess. Don't be shy, just say something. Also wrong, it's fine. Yeah, go for it. Good, it's the number of data, okay? So the FK table in general is a tensor which has shape like nx, where this is the interpolation grid dimension, n data, and n flavor. Here, and we have just one flavor, just T3, so this dimension is not there, and so you have, well, the transpose of this thing, n data and nx, okay? So in order to compute your prediction, you just apply this linear map to the vector of values of the PDF, okay? And in NumPy, you can do this with this syntax, fk hat f, okay? So this gives you some central values, and then you want to plot them and to compare them with experimental data. So when you do this kind of plots, it's convenient to normalize everything. In this case, for example, the experimental data. So that in blue, you see it's 1 because everything is normalized to experimental data. So the blue stuff, the blue line here represents the central value of the data. The error is, well, okay, this is wrong, but anyway, it's what I did. It's it's the diagonal entries of the covariance matrix, okay? Square root, normalized to the data. Here I'm missing correlation, but it's just to produce a plot that we can look at, okay? And in red is the theory predictions. Why I'm saying that it's wrong? Because I'm missing out correlations. Okay, so actually you should compute some shift and shift the thing, but who cares, okay? And in red, you have actually the results of this FK applied to F, okay? Normalized to the data. So what do you see from this plot? You see that the experimental data are described by this PDF within the experimental uncertainty, right? Okay. Yeah. Mm-hmm. Show me. No, but this is FK grid. So FK grid has dimension 50 because it's the grid of the FK table, which is the interpolation grid. While the FK table is a big FK. And if you do big FK shape, you will find, yeah, 2000 or whatever. Big FK. Tutto maiuscolo. Esatto. Esatto. Okay, question on this? Okay, let's look also at the other one together. I think it's probably more interesting if we go quickly on these exercises and then. So the second part was to compute the chi-square. Okay. So here I've written two functions. The first one, which does the inversion of a matrix. I mean, you can forget about that, and you can use just SciPy to do the inversion of a matrix. The reason I'm doing the inversion of the matrix by myself is just because it's good practice to invert your matrices by yourself without inverting them using a black box. And in particular, when you invert a matrix, just don't invert it, just decompose it, and then you invert the eigenvalues. If you use SciPy, invert, or whatever, it will do Cholesky. And many times, you will get numerical problems. If you do this, you have more control. So just a rule for life, don't invert matrix. But anyway, for this exercise, you can invert matrix also using SciPy. And then the last function is, I mean, you take, you just write a function which takes as input y, which is the central values of the data, central values for theory prediction, and the inverse of the covariance matrix. Don't take as input the covariance matrix by itself, because otherwise then you have to invert it every time inside the chi-square. You will be calling the chi-square thousands of times, and then you will be inverting the same matrix thousands of times, and your code will be super slow. So invert it outside. The experimental covariance matrix is a constant, and you can do this outside of the function. Okay? So you take this as input, you compute this shift between central values, and then n data is just, so the number of data. We are normalizing the chi-square to the number of data. It's not really necessary, but I'm doing it anyway. Is the size on y, and then casting it to float 32, otherwise the code will crash. Because, yes, because if you read the Keras documentation, you see that you have to do this. And then you combine these things just doing dot products. And the syntax is this one, and then again, I'm casting, no, I'm not casting, it's already float 32. Okay, so, okay, I mean, nothing interesting. I mean, it's a kind of stupid exercise. I mean, you sit down 10 minutes, you look at the solution, you convince yourself that it's like this, and nothing to learn here. It was just to make you play a little bit with the code. Okay, so now I'll do this. I'll copy this thing so that your code should run. I'll copy this thing. So this is in another notebook that you cannot see, which is called solutions. So I'll copy these in the notebook that you can see. I'll save it. I'm not sure if this is gonna work. So try to close the notebook and then click again on the link that Alessandro sent you before, so that to open the notebook again, freshly new. And yeah, you should see this. If not, I don't know. Yeah, you see it? Okay, cool. Okay, so now you will probably have to rerun again the notebook from the start. Please do it. So I'll do it myself as well here. So now that we have built the fatal, okay. Now that we have, oh yeah, sure, right. Here. So anyway, at the end, so we'll have two notebooks. At the end of each day of tutorial, so basically tonight and Thursday, I will, where is exercise one? I will basically upload at the end of this same notebook also the solutions, so that, yeah, so that in case then you're interested in looking at it again, you have. Okay, I've also uploaded the solution to exercise one, so you can again look at it. Okay. Are you all with me? Kind of? Okay. So we have built this function for the chi-square. And here, just to check that things works, I'm computing the chi-square between the data and just the theory prediction computed using a randomly initialized network, because we have not done any training here. And you see that we are getting 2.13, so not so bad for it to be kind of random numbers. The reason is that the errors are so huge. How much? Oh, yeah, so it's already a good fit. So that's it, no training required. So, okay, now let's see how to do the training. So first, so what's gonna be the input of the network? So the real input of the network. So I told you that you start from a real input. Yeah, just guess. So we have everything set up, right? We have the experimental data, the experimental uncertainties, we have a chi-square function, we have a network, and then we have an interpolation grid. So we need a real input, which goes through our network, which then will spit out our parameterization for the PDF. These theta are the free parameters of the network that then is going to be convoluted with FK table in order to give us the observable. So who is this input? X, but who is X? Well, yeah. No, it's the X of is the interpolation grid, right? So at the end, you want the network evaluated where? In the points that defines the FK table. So in this interpolation grid. So the input of the network is the interpolation grid. The interpolation grid goes through the network. So this is a vector of points. Exactly. Each point goes independently through the network. And then at the end, you have the PDF, I mean, your parameterization, evaluated on each of these points. Right? X 50. 50. And at this point, this will be 50 values of the randomly initialized network. Then these 50 points are convoluted with the FK table. So basically, this linear transformation is applied to this vector. And this gives you your observable. Okay? So you see that here I'm defining this X input. I'm defining it from the grid of the FK table, so the interpolation grid. And I'm adding a dimension. Why am I adding a dimension? Okay, yeah, say it. So basically, I want, if you do this, you can choose to do it either sequentially or in parallel. Sequentially would be kind of dumb. Also because, I mean, this kind of NumPy and so on is done exactly to parallelize this thing. So by adding a dimension, basically you're just giving this array directly. So instead of giving each component as input singularly to the PDF and go to through a for loop, you give it an array which has that shape, which already contains all the grid of the FK table, and then each components go in parallel through the network. Okay? And so the output actually of the network is not a real number, it's your 50 real numbers that then are convoluted in a single step with the FK table. Okay? So this is why I'm adding with this notion, I'm adding a dimension, okay? Which is empty, but it's doing that, okay? Then what I do here, I define this X output, which is basically just a grid that I will be used to plot the PDF at the end. So at the end, you will have your trained model, okay? So a neural network where all the free parameters can be constrained. And then you can use this trained model to plot your PDF, okay? On whatever X points you want, not only on the interpolation grid. And this is the grid I'm gonna use to do this plot. No, that's the point, right? You're really learning a continuous function. So the interpolation grid is what enters in the training. But then at the end, you have a trained model, and the neural network can be evaluated everywhere in X. And indeed, when you deliver your set on LHCPDF, it's not that they deliver it on the grid of your FK table. They deliver it on their on their specific grid. Okay. Are you following? 60%? 60%. Okay. More than 40, though. I mean, more than 50, so it's good. Okay. So, very questions? No? You're very shy. Okay, well, I'll keep talking. If stop me when something is not. I mean, the thing, I don't want you to understand a single line of code. If you're not familiar with, not only with Python, but with the specific packages, I'm not expecting you to understand, also because it's a matter of syntax, okay? But I want you to understand the concept, okay? So how clear are the concepts? 90%. 80. 80, okay. Okay, good. So let's see what happens actually. How do we do the training? So at this point, we have randomly initialized network, okay, which has been convoluted with the FK table in order to do the theory prediction for our data. We have the loss function, okay? So chi-square of theta. We want to minimize this, okay? We want to minimize the chi-square. How is this done? So again, it's a completely solved problem, and there are many ways of doing it. What happens in this cell is that we minimize it using a minimizer which is called Adam, which is based on gradient descent. It means that basically you have your loss function, which is a function of the four parameters of the network. You compute the gradient of this object with respect to the free parameters, okay? And then you update this object following the gradient, minus the gradient. Plus minus, I never remember. Okay, but you get what I mean, right? You've already seen this kind of stuff. So the point is that we are using a neural network. So computing the gradient of something which is a function of 700 parameters can be kind of challenging, but again, it's a completely solved problem. There is this algorithm which is called backpropagation, which is basically not so clever recursive application of the chain rule to do derivatives that you learn in the first class of analysis. I mean, if you sit down, you can rederive it by yourself. So there is this algorithm to compute the derivative of this network. You compute it, and then you do gradient descent. So you move towards the direction that is pointed by the gradients, towards a minimum and not towards a maximum or whatever. And you repeat this for a number of epochs. So the epochs, it's basically each step of your minimization algorithm within which all the data are scanned once. Okay?
How do you know that when you go down the gradient,
Yeah, of course, it's one I don't. So there are ways to try to. So so the question is how you're sure that you're not stuck in local minima, right? So like you could have so in a one-dimensional space you could have that your loss function is something like this, so the true minimum is here, but you could end up being here, and here we are in a 700 or whatever dimensional space. So actually, it's going to be a mess. So in general, at least for when using a neural network, it's not that there is a single minimum. There is a population of minimum. Some of them correspond to not fully trained model or like a bad trained version of the model. But then you have a population of good minimum. The point is that when you do a neural net fit, there is not a correct solution. If you run multiple times the same minimization, just initializing from different points, you will end up for sure in a different minimum. The point is, okay, then what can I do? Is it wrong? No, it's not wrong. It's just life. What can I do in order to avoid being trapped in something like this when clearly it's here? So there are different ways. One way you can, and it happens at different level. You can kind of regularize your, there are ways to basically boost the gradient every now and then. So it means that, say that you're stuck here, bam, 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 you do a boost which allows you to overcome the minimum in which you're with. And so there are solutions like this, and again, there is a full zoology of this kind of stuff that you can act with these things at the level of your minimizer. But then also, I mean, we will see later. Well, I don't know if we'll see it later today. We will see maybe Thursday. I don't know. So usually you don't train your set on your model on the full set of data. You split it, you have a training set and a validation set, and you perform the training on just a subset of the data you have. This is, if you want, is actually also a way to avoid local minima, meaning that you're computing the loss on the training, but in the meantime, you're keeping an eye also on the loss on the validation. And you're stopping the training, not when you reach the minimum of the training, but you reach the minimum of the validation. And this somehow, if you want, is again helping you in preventing some local minima, which would correspond to overfit in this case. So, I mean, there are different ways of answering to your question. It's a different level. Keep in mind that also this stuff, it's, there is a certain amount of cooking involved. So you have to learn tricks, things that sometimes works, sometimes not. Sometimes you should go to, there is not like a specific way to do things. If you want to comment, jump in.
Maybe it's worth saying that, of course, here the problem is relatively simple.
Yeah.
But of course, if you were dealing with the real data like the problem that Tommaso showed before, then the problem, you say, is much more serious.
Yeah.
And then, like Tommaso was saying, this is a known problem for which there is a number of solutions. So one is the one that Tommaso said of having a little kick. Other solutions correspond to have adaptive gradients. So for example, if in the plot you said you computed the gradient with a small range or a long range, if the range was big enough, then you get a different gradient than you jump on the other side. And so there are maybe half a dozen.
And actually, some of these are already. So this Adam algorithm, I think, is already implemented. This in the Bell. Yeah. For sure. But well, if you take like a subset of data, actually you're changing the loss function, right? So I mean, if you plot it, you get some. If you could plot a 700-dimensional, something living in that dimension, you would see something totally different. You've just changed the minimization thing you're doing. But that's the point. You're not expanding around a single minimum. There is not a single minimum. There is a population of minimum, and there is not a correct answer. If you run, now we will produce a code which fit the central value of the PDF. If you run it multiple times, you will find different things, but all of them describe equally well the data. Yes, I mean, this algorithm, you mean, yeah. If you want, yes. If you want, yes, totally. Yeah, it's exactly that.
This is related to the question that Alessandro was asking before, namely how do you determine the architecture of the neural network? So the full answer to the question is that both the architecture of the neural network and the minimization earlier you saw in the code that there was some initialization, right? So the initialization is a property which is, well, of the neural network, but really also of the minimization.
Yeah,
because
because
where you
it's
start to minimize. And for example, if you notice the line in the code, it says something like random norms. You could take instead random minimum, for example. And then all these are
here.
hyperopt parameters. How do you hyperopt? Well, like you correctly said, this is an inverse problem. So you have to define some metric in the space of possible results such that you hyper-optimize with respect to that. And now this is a simple example. So here this is not done, but in a real-world scenario, you have to first define a previous procedure where you have to define a loss function at the level of hyper-optimization. And the loss function at the level of hyper-optimization, for example, could be that your uncertainties are not small, rather big. So, for example, that a methodology that gives some slightly bigger uncertainty while giving the same quality, fit quality to the central data is better. But then, like Tommaso was saying, there's no unique answer because strictly speaking, this is a ill-defined problem, and therefore, so you can work out a quantitative way of defining a hyper-optimization that gives some answer, meaning that you have, but that's a common thing in machine learning. I mean, you have to decide what is your optimal solution, but a priori, that depends on how you define the loss which corresponds to your optimal.
Should be. Well,
Yes and no, right?
you would like to. So let's say there is first a phase where you define the methodology, which is what we're supposed to be looking at today. But then you want to validate your methodology, and then you want to check exactly this. Or this is one of the things you want to check. So you want to check that the uncertainties you're quoting, and not that we have not. I've told you nothing yet about how you define uncertainties here. So for example, you want to find that your model produces uncertainties which are faithful. What do you mean?
But also you want your model say to generalize correctly to other data points that
Yeah.
you have not included. So for example, a model that goes through the central value of all points is probably not very good because it's likely not to generalize very well. That's a very stupid thing.
So there are a number of things that you want to check a posteriori, and that's part of the validation of your methodology, and it's what we are supposed to see. Sorry? Validation function, you mean the validation loss? Yeah, I mean, the validation loss is basically what you use to prevent overfitting. And then this is connected, of course, for example, to what Stefano was saying, that you want to be able to describe also a test data set and so on. And one of the way in which you try to make sure that this happens is, for example, defining this training validation split. But okay, so maybe we are throwing too many things on the fire. So we still have half an hour, so I would just maybe like to see the solution. So you're super tired. You just want to stop this? No. Yes. No. Feedback, I mean, flat. Okay. Well, I'll keep going for, 20, 30 minutes. So we have the chi-square. We were looking at at the validation here. So we build this object, theoretical prediction, that you see I'm defining this observable class, which was coded up here, which, if you look at the constructor here, takes as input the FK table, so that you store the FK table in the value of this function. Where is it? Here. Then you define, so this object here contains the neural network, the FK table, and the final value of your observable as a function of the three parameters. Then you define an optimizer. Again, this is syntax. I just want you to follow the concept. As an optimizer, I'm taking this Adam algorithm, and in particular, I have to choose a learning rate, which means basically the size of the step which is done at each iteration of the minimization. a number of epoch, which is the number of iteration I'm doing. I'm taking 500 just because random number, 500, and then we look at the result. And then what do? I do this training loop. So for each epoch, what do? I compute in this with statement, I'm computing the loss function. So I'm using the chi-square that I've defined before. I'm giving as input the data and the observables. I'm cutting out this extra dimension I've defined before because now I'm not interested in it anymore. I mean, never mind, it's not important. The point is that this is the observable as a function of the three parameters at that point in the training. Okay, so I build the loss function. I compute in this line the gradient of the loss function. So you see, this is all coming from this package I'm using. I mean, there's no need to understand what's going on under the carpet. Here I'm computing the gradients, and here in this line, I'm actually doing the training step. Okay? And here also I'm saving along the way the chi-square. So you see here I've created this empty list outside of the loop, and then at each step I'm appending to this list the numerical value of the chi-square. Why I'm doing this? Because then I want to check how the chi-square is evolving, how the loss function is evolving as a function of the epochs. Okay, whatever. So I can run this thing. Ah, okay. Okay, so you can, okay, but it's the same, but I've just removed this because I wanted you to do the exercise. So add this, just copy, create an empty list called however you want, just before the for loop. So you can call it my empty list equal, and then, I mean, I'm calling it training chi-square because it's the training chi-square, but, so, but you do have this, let me check. Yeah, correct. Okay, yeah, it's only the list which is missing. Okay, so add this list, and then you see in the after the optimizer object is called here. I mean, after apply gradients is called from the optimize object. Just with this syntax, just append to this list. So you're saving in the list the numerical value of the loss, and in order to get the numerical value, you have to do loss.numpy. The reason that you have to do this is that the loss at this point is some tensor which is defined using Keras, I don't know with what, and you want it to turn it in an NumPy object so that then your plotting code later on doesn't crash. Okay, so if you've done this, you can run it, and it will take a few seconds. So what is it happening? We are fitting the central values of the data. So we are determining the best values of the three parameters of our network. I mean, the values of the three parameters of the network that best describe the data. It's thinking. Okay, 28 seconds completed, and then I can redo this plot. Okay, so what am I plotting here? So this is the PDF, so this is X. So the black dot line is the reference PDF taken from the literature. So it's an NPI 4.0, which has been determined from 4,000 data points, whatever. The green one is what we've just determined from 200 and something points. So what do you notice? So it's so you notice that at large X, it's okay. Below 0.1, it's crap. Okay, why? Exactly, because if you remember the kinematic coverage, I mean, this is expected, okay? So below 0.1, we are just getting back what we put in. We are getting basically whatever the network, whatever the initial initialization of the network was giving us, okay? I mean, here is at small x, it's fully unconstrained. But at large x, we are getting a, I mean, it's not an it doesn't seem to be random numbers, okay? Then exercise 3, I'm gonna give the solution for this as well, and then you're gonna do the next one too, which is the difficult one. So I'm copying. By the way, you see, you can also start coding or generate with AI, so you can try. I've never tried this option. So if you do this, it will generate some code for you. So maybe it will just solve the exercise for you. But okay, here I'm putting the solution of exercise 3. So again, do the same thing as before, and you will see the code. So what I'm doing here, I'm defining a function which takes as input the list I've defined before, the one which was saving the chi-square at each iteration of the training, so at each epoch. And basically, I'm plotting this value against the number of epoch. So this is, you see, we start from a value which was already pretty good, actually, 1.6. But then we go down to 0. Something, okay? 0.6 or something. So you see, this is just showing that something is happening. We're actually doing what we thought we were doing. We're minimizing the chi-square, and you see that actually seems that like that around 150 just stops improving. We reach a certain value, so it means that we are in some minimum. I cannot really say if it is a good minimum or bad minimum, whatever, okay? So in this way, we have fitted the central value of the PDF. Yeah. Well, for this specific initialization of the network, yes. But try, I mean, just put here 100. Okay, but it might depend on the, I mean, in this notebook, it might depend on the way in which the network is initialized. I mean, if you start from already a decent value, you get, so let's see. No, you see, in this case, shit. But, I mean, let's see this. Okay, it's crashing. Yeah. So you see, it's working, but you can see that it's not done yet, okay? But so the question is, how do you decide that you're stopped? I mean, in this case, we are looking at a simple example, and we have an example from the literature. We can say, no, this one is crap. Probably we need to go farther. But in real life, where you don't know actually PDF, how do you decide? We'll see. No, not really. I mean, the way that usually is done is that the training length, so the number of epoch, is again one of these parameters entering, one of these hyperparameters entering the. Maybe, I don't know. I mean, there is also kind of line of research, which is a kind of more analytical study and understanding of this thing. I don't know if you can relate the training length with the number of data entering. I have no idea.
Because like we were saying earlier, I mean, there are many things that are already which have to do with architecture to minimize some original. I mean, generally you have a very large space of hyperparameters, and one of the things you discover is that there may be completely equivalent solutions which are very far in the space of parameters. So, for example, just to make a very simple example, if you have a very big architecture, you may need a more aggressive minimization, which has which moves faster in the gradient direction. But then, if you do that, then also you may be happy with the shorter term, because you don't need it very long.
But at this level, I mean, in this exercise, let's say, the way in which we will choose how to stop the training is actually doing this training validation split. So you start from a number of epoch which you're sure it's long enough 500 in this case. And then you say, okay, I minimize training loss. And in the meantime, I keep an eye on the validation loss. At the first, both of them are supposed to decrease, but at some point, the training loss will keep decreasing with the number of epoch. The validation loss will start either increasing or will saturate somehow. That's where I stop. And we will see this next time, I think.
Yeah, so I guess the answer I gave was a kind of modern answer.
Yeah.
But, in the past, for example, what you could do is you try to start as a rule of thumb by determining the architecture of the neural network based on the typical complexity of the problem you have. So you count the number of parameters that the neural network has. You know what is the typical number of parameters. So let's say for a PDF problem, probably I don't know 20 or 30 parameters is enough. So you pick a neural network that has 200 DLSAs. And then you start running a few test minimizations with some algorithm of your choice, and you look at that kind of shape, you do a lot, and then you determine what's a typical range which leads you to the answer, and then, again, you multiply that by some large factor, by 5, to make sure that, and then typically you have some stopping criterion that such that you don't train for a fixed length, but actually you stop earlier by using training validation, for example, and then you make sure that in most cases the stopping will happen before of the maximum training length. And this is actually
How we do things.
how
Yeah.
many people still do things. I mean, I heard many machine learning talks in which you ask people, why did you choose that architecture? And they say, tried that and it worked. And then you ask, but why did you pick the training length of 12? Because it usually, so it depends on how refined you want.
Your experience, your usual fits, how many epochs do you typically need, or do you typically explore?
I don't remember.
Yeah,
It depends on the. I mean, it's a hyper parameter.
optimization parameter for us now. So, if you ask me what is the value of the hyper optimization parameter in NNPDF 4.0, I can tell you, I mean, I don't remember the exact number, but it's of the order of 50,000.
50,000.
Yes.
We can look in the paper, but.
Actually, there is this table in which we have two vastly different hyperops. It's much earlier. It's section 2 or 3. Yeah, picking methodology.
Here.
Yeah, there is. Yes,
This one.
yeah, that table.
No, it's not this one. This one.
Okay, so you see, for example, these are so these two are completely equivalent things, and this has 17,000, this has 45,000, and they give the same answer, but this uses ADA minimization, this ADA delta, which are both adaptive gradient minimizers, and then well, you see the architecture, for example, this has a much bigger architecture, and there is a plot here somewhere that shows that the results are increasing.
Which plot are you talking about? At the PDF level.
Shows that the results are PDF plot that shows that they are no, that's the bad one.
That's a bad.
But one that shows that if you put on top of each other the PDF obtained with those two methodologies, they look.
Well, okay, whatever. You can look at the paper tonight.
But anyway, you saw one was 20,000, the other was 50,000. Tens of thousands. Yeah, but with the sort of architecture that you saw and with the
And just out of curiosity,
90, yes.
so it is maybe 50,000 epochs, but typically where do you have the minimum of the validation?
Well, again, the.
You saw you were showing.
Yeah, it's down here. Yeah, but again, it's something that.
Okay, so no, stop here. So, for example, yeah. So this is This is a histogram that shows you the distribution of training lengths.
So the final epoch, the epoch at which the fit is actually stopped.
So this is like saying that 20% stopped at 13,000. And then you can see that there is a little spike here, which means that this thing was going down, and we really decided to
Yeah.
cut it off here, because if you move it to the right, you get some outlier, which is slightly better fitted, because it would go down here, but it's not really worth the trouble. And that was decided not by us, but by the wrong. But the answer to your question is what is a typical training length? Well, you really don't. It's a maximum of this distance, so it's like 13,000.
This would be the number of books to get a good description of the training. But then,
No, this is
No, no.
this is the output. This is where the algorithm has stopped using cross-validation.
Using cross-validation.
The way
That, by the way, I mean, we are talking about cross-validation, but we have not introduced cross-validation yet.
is
So,
tomorrow's lecture, but actually not tomorrow, but Thursday.
yeah.
But Alessandro knows what I'm talking about. So anyway, this is the optimal training length. So there was a maximum, but this is the optimal. So the fits actually stop at mostly 30.
But okay, probably the takeaway message from this, I mean, also just looking at this notebook, is that when building this kind of methodologies, there are a number of little factors you can play around. These factors are called hyperparameters. And the challenge, if you want, is to choose to automatize the choosing of these hyperparameters in a way which makes sense from a statistical point of view. Okay, so that when you claim a certain property of your results, you have some backup based on math, if you want, and not some rule of thumb that someone who speaks better English than you can just turn around against you. Okay, that's probably the challenge and the takeaway message. Okay, so maybe I would maybe do a little summary of what we've seen today, and maybe I would stop here, because I mean, next point is how do we introduce uncertainty on this. So far we have fitted the central value of the experimental data, and we have produced this line, which now looks bad, but before it was looking nicer, okay? But the point is that, I mean, a line without uncertainty is not really giving you much information. So I mean, next topic, which is actually quite important, is how we introduce an error on this. But maybe since it's 7 minutes left, and I don't know how many of you are still with us, maybe I will just summarize what we've seen so far, and we'll take it back from here. Yeah, okay. So what have we seen? So we have introduced the main ingredients. So I mean, I'm just summarizing because next time we will really get back from here also in terms of the code, and then we will build like incrementally on this. So we have seen, okay, experimental data, okay? So we have loaded central values and experimental covariance metrics, and these were DIS data from BCDMS. Then we have said, okay, this data, so the structure function which is measured in these experiments is actually related, so I'm just writing it schematically, to a single PDF that we have called T3, okay, which is a non-single distribution, so it's decoupled from everything else, so it's an ideal toy scenario to study this problem. Then we've said, okay, let's parameterize T3. Then we have introduced FK table, which allows us to turn this convolution in actually a multiplication between a matrix and a vector, okay? This is pre-computed, and these are values of the PDF on an interpolation grid. okay? And this stuff contains all the physics, so it contains your perturbative computation, including the evolution of the PDF. Then we have introduced the neural networks. We have said that these are kind of ways of building a complex nonlinear parameterization in terms of a big number of parameters. And we have seen this code, which allows us to basically define our PDF in terms of the free parameters of the network, and then we have built theory prediction as a function of the free parameters using the FK table. Then we have introduced a loss function, which in our case was just the chi-square, okay, using our observable as a function of the free parameters of the network and using the experimental information. And then we have seen the training of this network on the central values of the data, okay? So we do the training, we determine our model. So at this point we can look at the PDF on the values of the parameters, let's call it star. These are the parameters after the fit, and we have produced well, the other plot, which was nicer, okay? And then we said, okay, at large X, it looked like it's working, at small x not, but we know why, because we don't have any data looking at the kinematic region. So next time is, what about uncertainties? So how do we define as an uncertainty for this guy? This guy is a continuous function, so the question, if you want, is how you define an uncertainty in a space of continuous function. And maybe you know it already. I mean, if you've run MatGraph or some Monte Carlo, you know at some point you have to choose the PDF, and you have to choose also the replica of the PDF. So you have to specify the LHA PDF index, and if you use an PDF object, you have 100 possibilities. Usually you pick replica 0, but then someone asks you about the PDF error, and then you have to rerun your things 100 times, or to do reweighting or whatever. So we will see this next time. And then after uncertainties also, we were talking about this training validation split. So we'll try to see what this means and how we can implement this in this model. And then in principle there would be another notebook. We'll see how far we get, where actually we say, okay, now we have defining our methodology. Are we really sure that we're not producing kind of random numbers? How can we actually validate this methodology, and how can we be confident and convince our people that we know what we're doing? And this is the validation part, and yeah, we'll see how much we manage to cover. So yeah, this is it. You will find these notebooks well on this link, and then I'll just upload the solution up to this point. Well, I already did, so yeah, no, I'll do nothing. So yeah.